Preetham, can you hear me? Bhaskar here.
Hello, I can hear you.
Hi. Yeah,
Hi.
okay. We can hear you. Yeah, that's great.
Hey Zoyu, hello. How are you? But I can't hear you.
Oh, sorry, I just mute myself.
Oh,
sorry.
yeah, right.
How is it?
Thank you for sharing.
Yeah. So how is it at IIT?
It's good.
It's
yeah,
good?
there are no students.
Okay.
Everything is online.
Okay.
And how are things in Israel?
No, I'm actually not in Israel.
Oh.
I'm actually back to China. I didn't tell you, I guess. I'm back to China. Okay. I have been in China for a long time, like 10 months.
Okay.
Yeah. So I think in Israel, like they have, I don't know if they are still in lockdown. So they had a lockdown, and then they opened up a little bit, and then the situation became quickly very bad, and they had to lock down again. So
okay.
Yeah.
In China, things are fine.
Yeah, it's back to normal. Yeah. Actually, I'm traveling this month, so in China, yeah.
Okay.
Yeah.
So in your session, I think there are 4 talks.
Okay.
Right, let me check.
Hello?
Yes, you have 4. Yeah, it's 3:30 to 4:30. So average is 15 minutes per talk.
So each talk, how long? 10 minutes or 12 minutes?
Right. Actually, we don't think of it as a talk because talk is already online. They have already uploaded the videos on YouTube.
Okay.
So this is just to remind the audience what the result is.
Okay.
And maybe the main ideas in the paper. So it's a pitch talk for 7-8 minutes. And then the remaining are questions from the audience.
Okay.
Yeah, so 8 minutes pitching and maybe 5 minutes, 7 minutes of questions. And then you switch to the next, proceed to the next.
Okay.
If there are more
hello.
questions and discussions, then we have given Slack channel and Gather subscribe. Yeah, those facilities are there. They have already been sent the link.
Hi, Zayu. Can you hear me? This is Pritam.
Yes.
Yeah.
If there are more questions and discussions, then we have given Slack channel.
Yes, I can hear you.
Yeah. So I made you the co-host. So actually, you can take over and introduce the speakers and all. So I'll be there on hand for any technical issues or anything.
Do I need to mute people before they each talk, or you will do it?
Just a moment. Let me.
No, I think unless there is any noise, it's okay. You don't have to mute or unmute.
Okay. Okay.
Because I think the audience size will be quite small.
Okay.
So even if you don't worry about mute, I think it will work fine.
Okay.
But yeah, we request the audience as default to keep themselves on mute.
What do you say? What?
No, we have requested the audience in the email to keep themselves on mute.
Okay.
But that we have already informed.
Yeah. So I think. So Zayu, I guess we can start the session then. So as I said, if there are any technical issues, I'll be there on hand. Along with,
Okay.
Swati also is here. So yeah. So over to you actually. Okay.
Okay. So let's start the session now. I'm Zoe Guo. I'm chairing this session. So welcome to session A1 of FSTTCS. We have 4 talks today in this session. The first speaker is, I guess, Talikapali Kavita, right? Is that how to pronounce your name? I'm not sure.
Yes.
Okay, so Kavita is an associate professor at the TFR working on graph algorithms and computational complexity. Today, she's going to tell us about mean cost popular matchings. Yeah, so if you're ready, you can start talk.
Thank you. Thank you. So my paper is on min cost popular matchings. Am I audible?
Yes,
Yes,
Kavita, we
I
can
can.
hear you. Yeah.
Thanks. Yeah, so the input here is a bipartite graph, as in this example here, where every vertex has a strict ranking of its neighbors. These numbers on edges, 1, 2, 3, so on, they show these ranks. This is actually called a marriage instance and a very well-studied model in two-sided matching markets, such as matching students to schools or doctors to hospitals. The classical problem studied here is that of finding a stable matching. As we all know, a matching is stable if it has no blocking edge. The blue matching here is unstable since the edge between the two middle vertices blocks it. The red matching is stable. The famous result by Galen Shapley shows that stable matchings always exist in a marriage instance, and the polytope of all stable matchings is easy to describe. And so the generic optimization problem here, that of finding a min-cost stable matching, has several efficient algorithms. However, stability can be quite restrictive. Even when there are exponentially many stable matchings, all of them have the same size and they leave the same vertices unmatched. In many applications, it may be a good idea to relax stability to a weaker notion so as to have a larger pool of feasible or admissible matchings. And popularity is a natural relaxation of stability. So we said every vertex has a ranking over all its neighbors. This extends naturally to a ranking over all matchings as follows. We say vertex P prefers matching M to matching M prime if it prefers its assignment in M to its assignment in M prime. So this enables us to compare two matchings by asking every vertex which of these two matchings it prefers, and let's count the number of vertices that prefer each matching. So let's have a comparison between the red and blue matchings. Here, the top two vertices say they're indifferent between the two matchings because they get the same assignment in both. The two middle vertices prefer the red matching, and the two bottom vertices prefer the blue matching. So this comparison is a tie. Let's compare the red and green matchings. Here, the red matching actually has 4 vertices that prefer it, and the green has only 2. So the red matching defeats the green matching, or it is better than the green matching. A popular matching is one that has no better matching. So it is undefeated by all matchings in such a head-to-head comparison between pairs of matchings. This notion was introduced by Gordon Force many years ago, where he observed that every stable matching is popular. Algorithmic questions in popular matchings have been studied for the last 10 years or so. And in fact, every stable matching is a min-size popular matching. And we also know efficient algorithms to find max-size popular matchings. However, the generic optimization problem here, finding a min-cost popular matching when there are edge costs, that is an NP-hard problem. Moreover, it's NP-hard to approximate this within any multiplicative factor. So we explored the question, are there fast exponential time algorithms for this problem? And we show an algorithm with running time 2 raised to n over 4 for finding a min-cost popular matching in a marriage instance. We also introduce a notion of approximate popularity. Let's call a matching semi-popular if it is undefeated by at least half the matchings in G. Let's recall that a popular matching is undefeated by all the matchings in G. So we show an efficient algorithm to find an almost semi-popular matching whose cost is at most twice the cost of a min-cost popular matching. So this is a bicriteria approximation algorithm. We use the LP framework for popular matchings. Corresponding to any matching M, there is a suitable edge weight function that depends on the matching M such that M is popular if and only if every perfect matching has weight at most 0. The LP that is dual to the max weight perfect matching LP, that's a very simple LP given here, that will be useful to us. This shows that every popular matching has a very simple certificate of its popularity. That's an optimal solution to this LP that's given by this vector alpha. It's a very simple vector, just n, it's an n tuple, and each coordinate, its values in 0, +1, -1, and sum of all alpha values is 0. So every popular matching has such a clean, simple dual certificate. In fact, we already know a 2 to the n algorithm for min-cost popular matching in a marriage instance. This follows from recent work. This paper did not explicitly tackle this problem. It tackled a popular matching problem in general graphs, not necessarily bipartite. However, the following algorithm follows from one of its subroutines. This algorithm goes through all dual certificates. Actually, it goes through all parity combinations for the n coordinates in a dual certificate. And for each parity combination, it asks for a min-cost popular matching that has a dual certificate whose parities are consistent with the combination that we have fixed. And such a popular matching can be computed in polynomial time via an appropriate stable matching algorithm. And we have totally 2 to the n such candidates. The least cost such stable matching leads us to a min-cost popular matching in G. We'll use the same outline. However, we speed this algorithm up quite a bit. The first idea to speed it up is very simple. We'll use a subgraph of G that's called the popular subgraph. The edge set of this subgraph is the set of all edges that belong to popular matchings in G. This edge set can be determined quite efficiently. In any dual certificate alpha, all vertices in the same connected component in this popular subgraph have the same parity of alpha values. And this implies that rather than regard individual vertices as our atomic units, it's much more efficient to regard entire connected components, non-trivial connected components in this subgraph as our atomic units. For isolated vertices here, there's no problem. Their alpha values are 0. That's a simple consequence of complementary slackness. And our main technical contribution is to show that, in fact, it's sufficient to regard connected components of size at least 4 in this subgraph as our atomic units. And this leads to the desired running time. In fact, it leads to a 2 to the p running time algorithm, where p is the number of components of size at least 4 in this popular subgraph. So our algorithm is as follows. For vertices in connected components of size exactly 2, they are free. They can take any alpha value in 0, +1, -1. It's easy to show there's no connected component of size 3 here. And for vertices in larger size connected components, that is size at least 4, we fix alpha values. And for each parity combination we come up with, we construct a new marriage instance and solve an appropriate stable matching problem in this new marriage instance. Our technical lemmas show an equivalence basically between certain stable matchings in this new instance and popular matchings in the original instance D that have a suitable dual certificate, that is one whose parities are consistent with what we fixed. This leads us to a 2 to the p running time algorithm to find a min-cost popular matching in D. All the details are in the proceedings version. Thank you.
Okay, thank you. Let's thank the speaker. Any questions? Yeah, I have a question. So you define this semi-popular matching. What if I want a matching that is at least as good as, say, 51% of our
Yeah, so
matchings?
that's an open question. I do not know
It's
the
an open question.
complexity. Yes, yes.
Okay.
Even I'm not even able to reach half here. I show an almost semi-popular matching. That is half minus epsilon for a given positive epsilon. And the running time depends on 1 over epsilon and the size of the graph. So I can't even reach 50%. So 51% is even harder.
Okay, okay.
So I do not know if it is hard. It's an open question.
Okay, thank you.
Thank you.
Yeah, I think we have several minutes before the next talk. So yeah, if you want to ask questions, you can ask now. So
Kavita, a quick question. So is there any hardness results known that, I mean, maybe not for 51%, but is there any hardness known for a large thing?
No. So the reviewers also asked me this question. No, I don't know of any hardness result. So can we go to 1 minus epsilon? That is what we want. In fact, ideally, we would like a matching whose cost is at most constant times cost of a min-cost popular matching, and that's undefeated by almost all matchings, like 1 minus epsilon fraction of matchings. I don't know the complexity. I hope it's not hard. I really don't know.
okay.
Hi.
Okay.
Hi, Kavita. This is Sanjukta. So
Hi.
I have a question.
Yeah.
So here the weights that you, so the cost that you have for the popular matching, if these are related to the ordinal preference, then is this problem still hard?
I don't have a ready answer. It's a nice question. I don't know.
Okay.
I really don't know.
Like
I'm
I'm
not an
asking
intuition
about the
also.
reduction that you give. Are they related or
No, they're not related actually.
Okay.
That's true. They're not related.
Mm.
The question was, if the costs and preferences are related, does the problem become easier?
Mm-hmm.
I don't know.
Okay.
I'll think about it, but right now I don't have an answer.
Mm-hmm.
Are there any more questions? Okay, I think we can move to next talk. Yeah. So the next talk is given by Christian Conrad. He's an assistant professor in the CS department at the University of Bristol. So today he's going to give a talk about constructing large matchings via query access to maximal matching oracle. So Christian, are you ready?
I'm ready. Thanks very much.
Okay. Yeah, you can start now.
Can you see my screen?
Yes.
That's good. So, okay, great. Thanks very much. So this is a joint work with Lydia Binti Khalil, who worked on this during her BSc thesis. Okay, so this talk is about, or this paper is about matchings. So I just want to recap the very basic definitions that we need and that we work with. So we are given a graph, and a matching is just a subset of non-adjacent edges. So like the first red edge that we see there. Now, there are two important notions. That's a maximal and a maximum matching. Now, maximal matching is one that cannot be enlarged by simply adding any edge outside the matching to it. Like on this path of length on 3 edges, the central edge is a maximal matching. Now, a maximum matching is one that is of largest size. So on this path of length with 3 edges, the 2 outside edges, they form a maximum matching. And there's this important and property that every maximal matching in a graph is at least of size half the size of a maximum matching. Now, the reason why I'm stating this property is, so we've got the following objective here. We're generally interested in this paper in computing approximations to maximum matching that go beyond what would be given by a maximal matching. So maximal matching in terms of size would approximate the size of a maximum matching by a factor of 1/2. But we are interested in going beyond that and obtaining matchings that are larger than that. The key observation that motivated this work is the following. In many sort of resource constrained models, like in particular data streaming, so the main motivation comes from the data streaming model, but also in other models like distributed computing models, it's relatively easy often to compute a maximal matching, but it's often quite difficult to improve upon a maximal matching in terms of approximation for maximum matching. So to give a precise example, here's I give the example here of the data streaming model. So in the data streaming model, we see the a sequence of the edges of the input graph in arbitrary order. So an algorithm processes the edges of a graph in arbitrary order. Like in this example here, we have 4 edges. So the algorithm would see these 4 edges in any order. Now, the goal is to compute a matching in a single pass, so reading the sequence of edges while maintaining a relatively small memory. And the memory should be sublinear in the size of the input that we have, so a smaller little o of the number of edges. And we can see that this model, in fact, is perfectly suited to probably the most basic matching algorithm there is. So we can directly implement the greedy matching algorithm in this model. So the greedy matching algorithm would process the edges in arbitrary order, and you just put the current edge that you're looking at into your matching if that's possible. So if the 2 endpoints of this edge, they're not yet matched. Now, a matching can be up to size n, roughly, n². So this would only use space roughly order of n, and graphs can be much denser. So that would be sort of sometimes a sublinear space algorithm. So in the edge arrival streaming model, it's really easy to compute a 1/2 approximation to maximum matching in a single pass. Now, just to give you a quick overview what the current sort of state of the art here is. So I focus here in this overview on bipartite graphs. In the data streaming model, if we are only allowed to do a single pass over the edges, then we do not know how to improve on this approximation factor of 1/2 that is given by the greedy algorithm. We know how to improve on 1/2 if we are allowed to use 2 passes or 3 passes. So the best bounds are stated here, and we can basically improve by a little bit in 2 and 3 passes. We can get a 1 - epsilon approximation, but then the dependency on epsilon translates into the number of passes that we have here. Now, the key observation here is that if we look at all these algorithms designed in the data streaming model that work on few passes or even multiple passes, then they operate in a very similar way. So they, in each pass, they select a specific subgraph. This could be a vertex-induced subgraph or a subgraph spanned by some edges. And they run simply the greedy algorithm on this specific subgraph and collect edges by running the greedy algorithm. So in the end, in every pass, we collected some edges, and simply in the end, we output the largest matching that we can form among the edges that we have collected in these passes. And this is our research question here. We would like to know how large a matching can we compute if we solely invoke the greedy algorithm in each pass. So we are focusing on the class of algorithms that just run greedy in each pass.
Important, then by definition.
I'm sorry? Was that a question or was that an accident? Okay, let's continue, I guess. Here's the specific model that we study. So our model, we basically model these sort of algorithms that only run greedy in each pass with a matching game. And this matching game looks as follows. So the player can submit a query to an oracle in a round. And this query consists here of a subset of the vertices of the graph. The oracle needs to respond then with a maximal matching in the subgraph induced by the set of vertices. So this game goes on for a certain number of rounds, for all rounds. And in this way, the player sort of in every round can adaptively query a different set of vertices and collects edges. And in the end needs to output a matching that can be formed from these edges. Our goal is to understand what the trade-off here is between the number of rounds and the approximation ratio. Okay, and our results are mainly lower bound results in this model. So there are some existing upper bounds that fit perfectly into our model, and we basically prove for some of them that they're optimal. So in particular, our results are as follows. Now, it's not particularly surprising that in a single round using, we can query the entire input graph, then we obtain a maximal matching in the input graph. So this gives us a 1/2 approximation upper bound, and it's not very hard to see that this is optimal. Perhaps a little bit more interesting. So this, I should mention, holds for bipartite graphs as well. If we have 2 rounds available, then we cannot improve on this factor of 1/2. However, if we have 3 rounds available, then we can indeed get a 0.6 approximation, and we prove a matching lower bound to that. So that's our main result in this paper. The 0.6 approximation follows from a data streaming algorithm that was previously analyzed in the paper cited there. We also show that if we wanted to have a 1 minus epsilon approximation, then we need for that at least omega of 1 over epsilon rounds in bipartite graphs. Now, interestingly, the situation changes a lot when you go from bipartite graphs to general graphs, because there's a very strong lower bound. And this lower bound says that to improve on the approximation factor of 1/2 in general graphs, then in our matching game, you need omega of n rounds. So in particular, if you have only r rounds available, then there's a lower bound of 1/2 plus r over n. Okay, so regarding the techniques, so what we do is the following. So there are 2 results here that are annotated with an R, and they hold as well for randomized query algorithms. And the reason they hold for randomized query algorithms is essentially there are worst case graphs on which, even if the player knew the graph, to simply obtain the optimal edges by querying sort of vertex-induced subgraphs, you need a lot of rounds. So there are basically one worst case graph yields the specific result. So these bounds are in fact a bit easier to obtain. The quite difficult bound is the 0.6 lower bound. So this bound only holds for deterministic algorithms, and sort of the oracle would construct the hard input graph basically on the fly, which depend on the queries submitted by the player. So this results basically in many, many case distinctions. And so, sort of the difficult part is basically how to reduce the number of cases and to keep everything, make it possible that it's possible to analyze this sort of difficult setting. Okay, now what we want to do next is there's a very interesting question that we work on at the moment. So this model that we look at is a vertex query model. Every round consists of a query of a subset of vertices, and the matching returned is a maximal matching in the vertex-induced subgraph. What happens if the player can submit edge queries, and also what happens in sort of the randomized case if we have only a few rounds. There are also other related questions. For example, computing a maximum matching in this model is not clear. It is also not clear whether we can improve over this 1 over epsilon lower bound for computing a 1 minus epsilon approximation. And yeah, that's it. Thanks very much. And if you have any questions, I'd be happy to answer them.
Thank you. Any questions? Okay, so I think I have a question. In your slides, the first table you showed, there's a table that shows shows the dependence of approximation ratio on the number of rounds at the beginning. So is this for query for the greedy model you consider, or is for more general algorithms?
Yeah, so this is this table here shows the currently best results for the general data streaming setting. So if you look at the class of data streaming algorithms, but again, the curiosity here is that all algorithms fit into sort of the context of these greedy-like algorithms that just run greedy in every single round. And for this reason, we also see that the space dependency of these algorithms. So I didn't explicitly mention here how much space they use, but the space dependency is really just linear in n, because every matching computed in each pass is of size order of n, and the number of passes is constant. So these algorithms only use space order of n roughly.
Okay. Thank you.
Sure.
Is there any other question? Okay, let's thank the speaker.
Thanks very much.
So, our next speaker is Sanuka Roy, right? Sanuka Roy, she is a PhD student at the Institute of Mathematical Sciences in Chennai, and she does research on parameterized algorithms, computational social choice theory, and algorithmic game theory. So today, she will talk about, so the title of her talk is on the parameterized complexity of almost stable marriage. So Sanuka, are you ready? We can share the screen.
Can you see my screen?
It's black to me. Okay, I can see it now. Yeah. Yes. Yeah, I mean, if you're ready, you can start now, I think. Yeah.
Okay. Good afternoon, everybody. So I'll be giving this short speech for this paper on parameters complexity of almost stable marriage problem. And this is a joint work with Shushmita Pallavi, Saket, and Mehra. So the model that we consider, I think the previous Prabhita's talk also considered the same model. So this is matching under preference, and you have two sets of agents, or two disjoint sets of agents, and you want to assign one set to the other. For example, assigning doctors to hospitals, students to schools, and so on. And this kind of model is generally known as bipartite matching problem with two-sided preference, because the agents on each side have preference over a subset of the other side. And in general, any problem with rational agents, we assume that the agents will like to get matched to only to those other agents whom they prefer. Sorry. So if you don't understand the model, let me get into an example. So there you have two sets. One set is denoted as 1 to 4, the other is denoted as A to D, and they have preference over the other. So like here, the agent 1 have preference over a subset of the other side, which is A and B. He prefers A the most and B the least. Similarly here, A prefers 1 the most and 2 the least, and one would prefer to get matched to either A or B or remain unmatched. So now what could be an assignment between those two sets look like? So this is could be an assignment between these two sets. And but look at here that here C is matched to 3, but she prefers 4 more than her current partner. Similarly, 4 prefers C more than his current partner. So this kind of pairs or edges are called a blocking edge, and we call a matching stable if there is no such edge, that is no such blocking edge. So for this particular instance, this is a stable matching for this instance, and every stable matching for this instance is of size 2. So as we are seeing here that there are 4 agents in either sides, but we are matching only half of the agents. So the moral of the story is that stable matchings may not be perfect, so we want to have a better allocation. And what generally, as I told you in this examples of bipartite matching, that you are matching some resources, so we don't want them to go wasted, so we want a larger size matching. But how can we find a larger size matching? So the fact is that every stable matching matches the same set of agents, which implies that you cannot remain in the set of stable matchings and increase the size. So to increase the size, one obvious idea would be to sacrifice stability, but by how much and how do you measure the sacrifice that we are doing? So this could be, as we saw in the definition, that a matching is stable if there is no blocking edges. So we can measure it by how much blocking edges, how many blocking edges are we allowing. So to say this problem formally, you are given a bipartite graph where your sides are A and B, and you have preferences as I show in the example, and you are given 2 integers K and T. Now you are allowed to have at most K blocking edges, and you want to increase the size by T. So as I said, that every stable matching matches the same set of agents, they have the same size. So we want the size to be increased by T, and we are allowing at most K blocking edges. So this problem is NP hard, and this is not only NP hard, this is W1 hard when parameterized by K and T in a graph of maximum degree 3. And this is a polynomial time reduction. This is what shows that the problem is also NP hard. So okay, so this problem is hard. So then can we? But we want to have a better allocation. We want to have better allocation of the resources. So can we do what kind of tractable questions we can ask here? So to look at that, let us look at some properties of stable matching. So we know that there are many stable matchings there could be many stable matchings for an instance, but every stable matching matches the same set of agents. But there are agents have preference over the stable matchings. And what do I mean by this? So look at this instance, and there are 2 stable matchings that I am showing here. One is this black one, other is the blue one. And the black one, if you know, this is the main optimal basically. So all the agents on the left hand side prefers this black matching, whereas all the agents on the right hand side prefers this blue matching. So though double matching, and instead of asking that, can I find a matching whose size is T more and have at most K blocking edges? Now we are reducing our search space. We want to find a matching which is in the proximity of this favorite stable matching you have. And now we want to ask that, okay, in this proximity, can I have a matching whose size is T more than any stable matching and allows at most K blocking edges, has at most K blocking edges. So now this notion proximity, this is a vague term right now. So how can you define a proximity of your favorite stable matching? So you can think of a matching as a 0, 1 vector of length n square, right, where you put 1 if that corresponding edge is in the matching, 0 otherwise. So then you can write every stable matching or any matching of an instance using the 0, 1 vector. And a proximity can mean that you have the solution matching that you are finding is in a close Hamming distance of the favorite stable matching you have. So now if I am asking this question, so now since we saw that the original problem was hard, now we have reduced the search space, and now can I find this thing efficiently? Can we find a solution efficiently now? So this question stated formally would be again, you have this bipartite graph, and you now you are given 3 parameters. One is that the number of blocking edges you are allowed. that is k, the size you want to increase, that is t. And as I told you, if you think of it, that if you bound the Hamming distance, that actually translate to be bounding the symmetric difference between the given matching M and your solution matching. So so you are given a stable matching M, which is your favorite matching, right? And I want that the solution matching M star, its symmetric difference is bounded by at most Q. So this is basically a local search version of the first problem that you saw. And this problem is again NP hard and is again W1 hard parameterized by K plus T in a graph of maximum degree 3. And this is W1 hard parameterized by K plus T plus Q. So is this tractable? Yeah, if you are looking at parameter Q and D, then we can solve it in this much running time. And so this is a deterministic algorithm. We can get a random, so we can get a randomized algorithm for the same that would just shave off this log D factor. And yes, so we can, so I'll just directly, I'll not explain the algorithm here. I'll just directly go to the open
So
question.
a quick question, excuse
Yes.
me. So when you say it's NP hard, it's for unbounded QTR and QTD, or it's for
So
previous?
no, it's not para NP hard, but it's para NP hard for degree, because this is the same reduction. So the W hardness reduction is show for K plus T when the degree is bounded by 3. That is a polynomial time reduction, so that gives you NP hardness as well. So it's para NP hard for degree, but not bounded K and T.
Okay, thank you.
Okay. Yeah, so this paper, basically in this paper we studied this size versus stability trade-off, but there are many other parameters of the of a stable matching, or in this matching under preference model, like what about satisfaction versus stability trade-off? That is, we can define satisfaction of each of the agents, and now instead of finding a larger size matching, we want to satisfy, we want to increase or maximize the satisfaction, and we are ready to allow some blocking edges or trait stability. Similarly, this problem can be defined along with some utility functions, and there again you want to maximize the utility. So the same trade-off kind of results, a similar trade-off kind of results can be studied into this model. And with that, I would end this speech. If you have a question, you can ask me now, or you can write to me.
There is one question. Sorry, I just saw it from Sushanta.
Mm-hmm.
He asked, is it a requirement to have a partial preference list as with complete preference list?
Yes. So if you have complete preference list, then the matchings are always yeah. So if you have complete preference list,
please continue.
Yeah, then the matchings are always perfect. The stable matchings are perfect because it is always a stable matching is always a maximal matching. So the maximal matching itself is perfect in complete bipartite graphs. So then this question doesn't arise. It only arises in an incomplete preference list, but that is a general model to look at, because we can assume when you have large number of agents in both the sides, you cannot assume that the agents will be ranking giving a whole linear order of the other side. It can be assumed that that would be a subset. So
yeah, I guess he asked, he said that if the preference list is complete, then the problem seems polynomial time. Is that right?
The problem, I don't, so the problem does not exist, because the question is that the size, we are trying to say that can we increase the size. So in a complete bipartite graph, all the stable matchings are perfect. So they have full size. So the question doesn't exist there.
Okay. So last question I want to ask is that this algorithm assume you are given input stable matching, right? So you're when you define your algorithm, you define your problem, it assume a matching is given. So stable
For the
matching,
local search
stable
version, yes, it assumes that the matching is given, and we are searching in the neighborhood of that matching, in the proximity
I
of that
see.
matching.
But if you do not assume, like if you just want to find a matching
Right,
that is...
that is the first problem that I defined. So
okay.
this is the one, right? This is the one where we saw that this is also hard.
I see.
So that's why we came to reduce the search space.
There's also a question from Vishwa Prakash. He asked, is there any related work in the roommate setting?
No, there is some related work in the bipartite graph setting, as far as I remember. I don't remember if that is also in the roommate setting. So there they, instead of looking for any matching whose size is in more than stable matching, they are looking for a maximum matching in the graph whose size is more than the stable matching. Because as I said that the stable matching is a maximal matching. Okay, so there is another, there is a almost stable roommate problem is also defined. Yes, there are some results. So these are by Peter Peter Biro. He has this paper on this almost stable roommate also.
Okay.
And and one of our results also does not assume anything about bipartite graph, so it extends to roommate.
Rakesh Mohanty asked, what's the complexity? Can you be more specific? What's the question? He asked, what's the complexity? Maybe regarding your previous...
complexity for...
I think his question is above.
Yeah, so since this is hard in bipartite setting, it will be hard. I'm in the roommate setting as well. And do you want to, are you asking about some specific question? Like the local set version is something which we have defined. So
she asks, is there any optimum?
I don't think it has been.
She asked, is there any optimum offline algorithm for stable matching?
Optimum offline, yes. So if you want to find just any stable matching, that can be found in linear in the number of edges. That is the seminal paper by Gale and Shapley, which is the first algorithm in this book, Tardos's algorithms book, I think. So there is a polynomial time algorithm for finding any stable matching.
Okay.
I cannot see the questions actually. I'm not sure where should I go to see the questions. Okay, in the chat, right?
Any other questions? Okay, let's thank the speaker. So our last talk is given by, I think it's Aditi Dudeja. Is that the right way to pronounce it? I'm not sure.
Yeah.
So this is by okay. Yeah. So Aditi is a graduate student in the CS department at Rutgers University. And today she will talk about online matching with recourse random edge arrivals. So if you're ready, you can start now.
Yeah. Just give me a minute. Sorry.
Shanjukta, you need to stop sharing of your screen.
Yes, I'm.
Yeah. Let me check.
Okay. I think. Okay. Sorry. Is it stopped now?
Yes. Yeah.
Okay. Sorry. I think I'm just a minute. Sorry about that. So am I audible and can everyone see the slides?
Yeah, you can see it.
Right. Hi, everyone. I'll be talking about online matchings with recos and in the context of random edge arrivals. So let me first explain the model, the edge arrival model with recos. So what happens in the edge arrival model with recos is that the edges of the graph, they're revealed one at a time. And what an algorithm is supposed to do is that it's supposed to maintain a maximum matching throughout the time when the edges are revealed. And when an edge is inserted, for example, the size of the matching may increase. So the algorithm is required to maintain a maximum matching, which means it may have to augment the matching. And the goal is to always minimize the total number of changes that are made to the matching. And this is just called the recos. And this recos is precisely the length of the augmenting path that is taken to increase the size of the matching. So in such a model, what happens is that let me just say something about what is an upper bound on the recos. That's order n square. And the reason is that each time a new matching is created in the graph after the insertion of an edge, you can always take an augmenting path of length, something like n, and increase the size of the matching. And since the size of the matching can increase only n times because the total number of vertices are n, what will happen is that the total recos can be upper bounded by order n square. But the thing is that even in simple graphs, there's a strong lower bound in this model, in the sense that you can have an adversarial ordering of edges so that the total recos is omega n square. So for example, if you take a simple simple graph such as the path graph on let's say n edges or n vertices, this order of appearance of the edges can lead to a total recos of omega n square. So suppose first the middle edge arrives, and what the algorithm does is, now that the size of the maximum matching in the graph is 1, the graph takes an augmenting path of length 1 and maintains the maximum matching. When E2 arrives, then E1 is still matched at that point of time, and the maximum matching is of size 1. So it does nothing. When E3 arrives, the size of the maximum matching has increased to 3, and then it must take an augmenting path of length 3 to get a matching of size 2. And if you keep doing this, I mean, the alternate edges on each side of the path, they keep arriving. What happens is that after an alternate number of steps, you'll be taking an augmenting path, which is equal to the length of the path so far, to augment and increase the size of the matching. So in this case, the total number of changes that you're making is something like n square. So what we study is something called random arrival, where the edges don't arrive in a random order. Instead, sorry, the edges don't arrive in an adversarial order. Instead, the edges arrive in a random order. And the motivation is just that in many practical situations, unlikely that you have not only a difficult graph, but also a worst case ordering of the edges. So yeah, the model is precisely just that instead of an adversarial ordering of the edges are arriving one at a time randomly. So what we're going to measure is the expected recos in this case. And these are our results in this model. So for example, for the case of general graphs, this is a non-bipartite graph. The random arrival doesn't in fact help. We get a lower bound of omega n square over log n on expected recos. So I just like to remind you that the total recos is upper bounded by n square. So this is nearly, this is nearly matching the upper bound. So for the case of trees, we are able to get, and we're able to upper bound the recos by order n times log square n. And for the case of paths, for the special case of paths, we get an upper bound of order n log n. Further, for the case of trees, we show that these bounds are nearly tight. and there's a lower bound of omega n log n on the expected recurse. So let me just show you what the graph looks like. So this is what the lower bound graph looks like. So there's a collection of these complete graphs. These are these green things. They are complete graphs on something like log n vertices, and there are n over log n, many of them. And within each of these log n vertices, there are these special blue vertices that are connected via matching to these dangling vertices. And there are n over log n of these. Further, and each of these complete graphs, they're connected to each other in the form of a ring. And every pair of vertices, let's say in ki and ki plus 1, is connected to the other. So there's a complete bipartite graph between any two KIs. So this is what the lower bound graph looks like. So the intuition behind the lower bound proof is as follows. So if you look at, let's say, a point in time when, let's say, m by 4 edges have arrived, then, so let me just say something. So the total number of edges that are dangling, there's something like n over log n, right? And when you look at a point in time when, let's say, something like m over 4 edges have arrived, something like a constant fraction of the total number of dangling edges would have arrived. And what happens is that the graph so far contains a perfect matching. So the next time a dangling edge arrives and another dangling edge arrives, what happens is the size of the matching is increased. But in expectation, the two dangling edges are arriving quite far from each other. They're arriving at a distance n over log n from each other. So since there is a perfect matching in this graph, this is what we prove. There must be an augmenting path that sort of starts at ET1 and ends at ET2. And this augmenting path will have length at least n over log n. And the algorithm is forced to take this augmenting path and increase the size of the matching. So since there are at least a constant fraction of vertices of dangling edges that are still left to arrive, what I mean to say is that there are some n, they are like theta n over log n dangling edges that are still left to arrive. Yeah, there are, so we get a lower bound of n square over log n on the expected recurse. That's how the lower bound proof goes. So finally, I'd just like to tell you some open questions. So the lower bound that we got was for the case of non-bipartite graphs. And an important, I guess, a nice open question is that can you also get it for the case of bipartite graphs, the same lower bound? And the second lower bound question is that there is a gap of log n between the upper and lower bounds for the case of trees. And can this gap be closed? So these are the two open questions. That's pretty much it. And yeah, if there are any questions.
Okay, thank you. Are there any questions?
I think there's a question in the. Okay.
So what's the upper bound for, say, random graphs? Do you know better upper bound, better than n square?
When the graph is random?
Yeah, yeah.
Oh, like GNP or
I don't know, just any kind of random distribution.
Right. I see. I'm not sure. Yeah, I think for the case of okay, so right. So I think for the case of let's say random graphs, I think there's a threshold, and I think beyond that there is a perfect matching. So after that, you don't really increment, as far as I know. This is for the case of GNP. but I'm not sure what the total recourse will be in that case. I'm not exactly sure, but I feel like there's a threshold beyond which there is a perfect matching that's already existing. Sorry?
Sorry? Okay. Any other questions?
So there's a question in the chat. Does this hold for
Sushanta, yeah. Sushanta asks, does it hold for hypergraphs?
Right. So which one? I feel like the low bound will hold because I'm not sure about the upper bound, but I think the lower bound should hold for the case of hypergraphs. I don't think it's yeah, because yeah, I'm not sure about the upper bound, whether it will hold or not, but the lower bound should hold.
Okay, thank you. Any other questions? Okay, let's thank the speaker. So that's the end of this session. We are going to have a virtual coffee break, and you can join the virtual social instructions through the gather link in your chat box.
Yes, Zayu, thanks for sharing the session. Yeah, and thanks to all the speakers. As I just wrote on the chat, I mean, you are encouraged. So unfortunately, we are not able in a position to provide your coffee. You have to get that yourself. Sorry about that, but yeah, please do join the Gather virtual space, and we can have some interactions with each other. At least get some feel of it, of the real conference. So we'll be back after 15 minutes. Huh. So till then, let's enjoy our coffee and the social interactions. Okay. Yeah. Thank you, Zayu, once again.
Thank you.
Thank you, Zayu.
Hello, Pritam, are you there?
Yeah, Swati.
Yeah, okay.
I'm here.
So we can pause the video. Acha, you
Yeah,
have already.
I just paused the recording. Yeah.
You can share
let us
the poster.
make the co-hosts for the next session right now.
Yes, I'll just tell you the names.
Yeah.
Okay. It's Ravi Shankar.
Not here yet.
Okay. If in case he's not available, then Amit Kumar will be presenting.
They're also not here yet. Maybe I think they will join a bit later.
Yes.
Maybe we should do that after 5 10.
Yeah, it has to be started at 4:45. Now, ideally, maybe that's why.
Yeah.
Okay.
So
Erin, Karthik. I'll just check like who if
Karthik is here. Yeah, you can tell
Karthik
me
is
if
here.
the name is there.
Yes.
Yeah, I'll just make them the co-host.
And Erin is not yet here.
Not here.
Okay. Joshua.
No.
Not here. Okay. And Shreyas.
Shreyas is here. So I'm just making him a co-host. Karthik and Shreyas are here.
So I'll let you know once the other guys join, and then we can make them co-host.
Right. Okay.
And for this session chair will be Venkatesh Raman.
Okay. Yeah.
Okay.
Sure.
Hello, Pritam, you can share the screen, the poster. I can't see that here.
Yes, was doing that only. Yeah. Just a minute.
So, Preeta?
Hello? Hello,
Yes.
Preetham?
Yeah.
Yeah, so our session chair is here, and
Okay.
so is the first speaker,
Okay. Just,
Ravi Shankar.
yeah.
Hi, yeah, I am here. I can hear you.
Yes. Only two of the speakers are not here. Let me check if we have somebody else speaking today. Joshua and okay.
So should I share the screen and then give a quick? I mean,
Yeah, I think first speaker is here, so maybe you can start and introduce the session chair. Then I think he can take over.
Yeah.
As soon
So
as
I'll
the speaker
stop the
joins,
share
I'll
then.
let you know over call.
Should I stop my share then?
Yeah, I think we can do that.
So before the introduction, just let me know. I'll resume the recording.
So, who is speaking? Preeta?
I have resumed the recording.
Okay. Yeah, I just saw that.
Yeah, hi. Can you hear me? This is Venkatesh Raman.
Yeah, hi, Venkat. I can hear you.
Yes, you're audible. Yeah.
Hello, can you hear me?
Yes, I can hear you. Yeah.
Yeah, can you hear us? We can hear you.
Yes, we can hear.
Yeah. We can hear you.
Hello, can you hear me?
Yeah, I can hear you.
Okay, we'll write over chat. You can hear.
Yeah, speak now.
Yeah. Hello.
Okay.
We can hear you. Can you?
Now
hear
I
me?
can. Yeah.
Okay. Yeah. Great.
I actually see Erin Taylor. You can make him a co-host as well. Joshua is the person we are missing, but his talk is fourth talk, so it's fine. We are fine.
Yes, I'll add him once he joins. Yeah. So I think now all our speakers are here, right?
Yeah.
Okay, should we start? Welcome to session A2 of FSTTCS. I am Venkatesh Raman from the Institute of Mathematical Sciences, Chennai. So there are 5 talks in this session. The first talk is titled Online Carpooling Using Expander Decompositions, and it's authored by Anupam Gupta, Ravi Shankar Krishnaswamy, Amit Kumar, and Sahil Singla. And Ravi Shankar is going to give the talk. Over to you, Ravi.
Can you guys hear me?
Yeah, we can hear you.
Okay, let me share the screen. And it's 15 minutes, right? Or
yes, 10 minutes plus questions.
10 plus. Okay. Okay. And hopefully you can see the screen also.
Yeah, we can.
Okay. So this talk I'll be talking about this carpooling problem, also called edge orientation problem, and we'll hopefully go over like online algorithms for this, which have online algorithms which work in a stochastic model with reasonable guarantees. So what is the problem? I'll just quickly talk. I won't have time to go over the techniques at all, but the YouTube link has a slightly longer video. So what's the problem? So we are given a collection of vertices and edges that are arriving online between these pairs of vertices. And they could form a multigraph. So maybe the same edge can come later again. That's okay. It's allowed. The goal is when a vertex, when an edge arrives, we have to orient it either from U to V or V to U. And the objective is to minimize the maximum discrepancy for every vertex. And the discrepancy is simply the in degree minus out degree in the current orientation. So we want to minimize the max over all vertices V of the absolute value of this discrepancy. And informally, it ensures that the orientation is as balanced as possible. So it says that every vertex has roughly equal number of in edges and out edges. And this is the edge orientation problem. So here is a little toy example here. So you have these vertices U1, U2, U3, U4.
Hello?
And so, yeah.
Yes, Bhaskar.
Sorry, is that a question?
Yes, we started at 4:45 exactly.
Okay. Yeah.
It's,
so yeah.
Live streaming is on.
Okay.
And it's saying, okay, it's showing live.
Okay. So you are able to see the screen, right?
Yeah. Go ahead, Ravi. Yeah.
Okay. Yeah. So here, it's here is a small example. So there are 4 vertices, and the first edge that arrives is the edge U1, U2, and the algorithm may decide to orient it from U1 to U2. And the next edge is U3, U4, and the algorithm might decide to orient it from U4 to U3. And now the third edge could be the edge U to U3. And notice that no matter how you orient it, one vertex will have a discrepancy of 2. And so this is clearly there is, I mean, if you had better information and if you were doing the orientation in hindsight, you would have done a different orientation where the maximum discrepancy is only 1. The U1 and U4 have a discrepancy of 1. U2 and U3 are perfectly balanced. So this is the loss of information that the online algorithm faces when it tries to do the orientation. And this is what we are trying to do. We are trying to find an online orientation which has as low a discrepancy as possible. So why is it a carpooling problem? You can think of vertices as a collection of people, and the edges are just pairs of people who wish to ride together on any given day. So maybe there are 2 people who live close to each other and commute to the same office. So edges are just that they choose to go to office on a particular day together. And orientation just decides who gets to drive and whose car is going to be used. So fair, low discrepancy solution ensures that every person is driving for the same amount of days as he or she is being driven. So the vehicle usage is fair. So of course, the way I said it, it's very simple problem, the simplistic model. You could generalize it to edges having weights, and also hypergraphs denote 3 or more people to share a ride together. But for this talk, I'm going to just consider the simplest setting for unweighted graphs. So what's known for this problem? Offline, you can actually do like the optimal solution, which is a very easy solution to get a discrepancy of 0, 1, or -1. The idea is very simple. You just take a cycle in the graph, you peel it out because you can orient it in a consistent manner. It adds no discrepancy to any vertex. And what you will be left with is a tree. And again, you can peel out a maximal path from leaf to leaf in this tree, oriented in a consistent manner. Only the leaves get any discrepancy added, or plus or -1. Internal vertices have no discrepancy change. And this will ensure that every vertex has 0, 1, or -1. Online, what's known, you could do a random assignment. You could randomly assign an edge, orient an edge with the ±1 half probability. The problem is the expectation is very good, but the variance is very high. So after t arrivals, some vertex will have a discrepancy of square root of t with high probability. So, and the goal here is to try to minimize the dependence on t, because t could be very large. Remember, we are allowing multigraphs, so t could be much more than n square. And this problem was considered in the 90s by Aita et al. And they show the following. They were the first people to consider this problem. So they first show a very nice, surprising lower bound, which says that if your algorithm is deterministic, then it must incur a high discrepancy. So there must be like some vertex which has a discrepancy of theta n. You can't have a deterministic algorithm that has logarithmic discrepancy. Then they show a simple randomized algorithm which can get rid of this variance problem and get a discrepancy of square root of n log n. And it's a very simple algorithm, and I won't go into the details. And if you think about it for 2 minutes, you can come up with it. So, but for the special case, they have another nice interesting result. They also consider a stochastic version of this online problem, where they assume that the arrivals are not completely adversarial. They're going to be uniformly random edges from the complete graph on n vertices. So each new arrival is going to be a uniformly random edge. And for this, they can get an algorithm which has a discrepancy of theta of log n over a sequence of variables. So it's an expectation result. So for any t, the expected discrepancy at that time t is going to be theta of log n, max over all vertices. But the nice thing is they can beat the square root n and square root t dependencies and so on. So what we do is we consider the stochastic model and generalize their result in from complete graphs to arbitrary graphs. So given any graph G, suppose every new edge is a random sample from this graph G, then we have an algorithm which can find an orientation with a maximum discrepancy of polylog n comma t over a sequence of t variables. It says that max over all time, max over all vertices, the discrepancy of any vertex at that time, intermediate time is at most polylog of n comma t. So like I said, it improves over the Ita et al. Result in two different directions. I mean, okay, so one is strict improvement because it works, not okay, neither is strict. So it extends from the G being a complete graph to arbitrary graphs. It allows arbitrary graphs. And if you look at their result for arbitrary graphs, you have to get a square root n discrepancy, whereas this gets a polylog n discrepancy. But they don't assume any stochasticity for their arbitrary arrivals case, whereas we assume that the edges are sampled IID from this known graph G upfront. Okay, so any questions? Okay, so I'll just very briefly go over the algorithm. So the algorithm is a very natural algorithm. So we just consider the greedy algorithm first, right? So when when a new edge arrives, you can request it oriented from the higher discrepancy vertex to the lower discrepancy vertex. And how you might analyze this is through like a soft max potential, which is by now become a very classical way of analyzing such algorithms. So you take the sum over all vertices of the e raised to the discrepancy of this v, and try to show that this has bounded growth, and eventually if this has a bounded growth, then every vertex will have low discrepancy. So notice that if the discrepancy difference between u and v is at least 2, then the soft max potential actually comes down. The greedy algorithm does the right thing, because if it was like 10 and 6, then it would make it 9 and 7, and then you're in good shape. The potential actually comes down. But the bad case is when the two vertices have the same discrepancy, then this potential could go up. And the increase really depends on how high the current discrepancy is. Because if it was like 100 and 100, then it becomes 99 and 101. It actually has gone up. You can see just with the convexity of this function. And this is the intuition for the deterministic lower bound that Ita et al. Use. So because it's a deterministic lower bound, and suppose all discrepancies are in a small range between say minus n over 2 and n over 2, there will always be two vertices with the same discrepancy value. Then the adversary can request that as the next request, and the potential can keep increasing. And then eventually one of the endpoints has to be hit, and this is exact lower bound equation. And what we do to circumvent this adversary is the new arrivals are stochastic from a graph, right? So it can't predict the two vertices of equal discrepancy, and that comes to help us. Right? So maybe the greedy algorithm actually works. So that's how we come up with our algorithm. So remember I said that the Ita et al. Paper can actually handle complete graphs. The arrivals are from a complete graph. We take the nicest generalization of that to expander graphs and say that first the greedy algorithm works well for expander graphs when the edges are sampled from expander graphs. And next we show that we can use recent machinery which can decompose arbitrary graphs into a disjoint union of expanders and then apply the greedy algorithm locally on each expander. So this is our overall high-level roadmap. So to show that the greedy algorithm works on expanders, we use the soft max potential that I just spoke about, and we bound the growth rate of the soft max potential. And here we actually, our analysis is inspired by another very nice paper by Perez et al., which considers this classical problem, right? This balls and bills problem. And they show that, so there's also this extension to balls and bills, which is the power of two choices that many of you might have heard about, which says that if at each point in time when a new ball arrives, you sample two uniformly random bins and throw the ball into the lighter loaded bin, that has much better max load distribution as compared to just a single uniformly random bin. So this Perez et al. Paper extends this to say that instead of sampling two uniformly random bins, what if the two bins are sampled as the edge of a uniformly random edge from an expander graph? They show that even this process has good characteristics, and they analyze this process. But they study something called a 1 plus beta choice process on expander graphs. Oh, sorry, let me get to that a little later. So the real question is, since they look at expander graphs and their process is slightly different, it's the balls and bills process, we try to adapt their analysis to work for edges which are sampled uniformly from an expander for the discrepancy process. And indeed we can. And the way we do that is through this process through an intermediate process, which is again very interesting, called the 1 plus beta process. And unfortunately, I don't have time to go into that. But the longer YouTube video has details of this. Okay, so it's like an intermediate process that is nice enough to analyze, and at the same time stochastically dominates the original process that we are interested in. So it's like a coupling argument. And we follow this template to show that the greedy algorithm works well on expanders. Okay, and I'll skip this part. This is the analysis of the 1 plus beta process, which is the intermediate process, which is easy to analyze. The second step is the expanded decomposition, and there are lots of recent works that are very nicely applicable to our circumstance, to our situation. So what we use is the following. There is an efficient algorithm which, when given a graph G, can partition it into a collection of expanders, disjoint union of expanders, which at each graph is an expander, each HI. And moreover, each HI is weakly regular. What we want is not just expanders. We also want this property that every graph that the partitioning outputs should be almost regular. So we don't get exact regularity, because if the input graph is a star, for example, you can't do anything, because the max degree and the min degree can be very different. But what this decomposition can ensure is that the minimum degree of this graph is at least at least a reasonable fraction of its average degree. It says nothing about the max degree, but this turns out to be sufficient for analyzing the 1 plus beta process. And moreover, each vertex appears in a small number of these expanders. So it's an edge disjoint union, but each vertex also appears in a bounded number of expanders. So here is the final algorithm that we do.
Maybe Ravi, sorry for the interruption.
Yeah. Sorry, what did you say? We're out of time, right?
Yeah, you should wrap up.
Okay, I'm going to wrap up in 1 minute. Okay. So what we say is that we run this expanded decomposition to get these graphs in the offline step. And when an edge arrives, we see which expander it belongs to, and then put it through the greedy process on that expander, locally on that expander alone. And then our final solution is just a concatenation of all these orientations. And so each edge decides which expander to go to based on the decomposition, and then the greedy process is run locally on that expander, and then we are done. And to conclude, we can study general graphs, IID arrivals. So how about non-IID arrivals? That would have been an interesting question, but recently there's a breakthrough result by Always et al. We can not only can solve this problem, but a much more general problem using a very nice and elegant algorithm, and maybe we can chat about it offline, or there I can point the link to the paper. Okay. So that's pretty much what I wanted to talk. Thank you.
Okay, thank you. Are there any questions? Maybe we have time for one question, maybe. You put it in the chat or unmute and talk. So what about in hypergraphs? What is known?
So yeah, so that's a good question. So the original paper actually studied hypergraphs, and they had a way to analyze hypergraphs. Actually, they could, if I'm not mistaken, they had a way to. Okay, I'll think about it and let you know. But it's actually a good question, and I think we can use original paper's techniques combined with our techniques to get something. I'm not exactly, I can't commit to what we can get, but the problem is interesting, right? So in hypergraphs, you want to look at the fairness in a different way. Like each person should be driving for the fair share, which is where the fairness is now, there's no incoming and outgoing. It's just you designate a driver for a subset of people, and each person should be designated driver roughly, like if it's a 3 regular hypergraph, each person should be designated driver 1/3 of the times.
Yeah.
So that's the sort of fairness, and we can get guarantees. Maybe we can take it offline. I can tell you what sort of.
Okay. Okay. Thanks again.
Yeah. Thank you very much. I'll stop sharing.
The next talk is titled Clustering Under Perturbation Stability in Near Linear Time. And it's authored by Erin Taylor, Pankaj Agarwal, Kamesh Munagala, Mo Wells, and Xianqi Chang. And Erin is going to give the talk. Erin, over to you.
Thanks. I'll share my screen. Okay. Can you see it okay?
Yeah.
Okay. Right. So this is joint work with Pankaj Agarwal, Xianqi Chang, Kamesh Munagala, and Mo Wells. So we're looking at a problem that we've probably all seen before. So a center-based K clustering problem, where we have a set of endpoints in Euclidean space, and we want to find K clusters And a solution will be a set of centers.
Sorry, are you moving the slides? We don't see
Yeah.
next slides yet.
So you still see the title slide?
You still see the title slide. Yeah, okay, yeah, now it's better. Thanks.
Okay. Let me try to full screen. So can you still see?
I don't think that we see the present mode that you're trying to show us.
Oh. Okay, I'll just use this then. Okay, so, right. So a solution is just a set of centers where each point of the original point set is assigned to its closest center, and we want to minimize the cost of the clustering. And so maybe the three most standard cost metrics are k-median, k-means, and k-center, where k-median is just the sum of distances, k-means is the sum of squares, and k-center, you're just minimizing the maximum distance. And we've also probably all seen that these problems are all NP hard, even when you limit yourself to Euclidean space. So maybe the natural next step to do is to compute an approximate clustering. And an approximate clustering will give you a guarantee on the cost of the approximate solution in comparison to the optimal solution. But structurally, you're not given a guarantee. So the actual partition of the approximate solution may be different than the optimal solution. So just here's an example with two clusters where you might run an approximation algorithm, and the actual clusters you return are very different than the optimal clusters. But again, these clustering problems are very widely used in practice, and even simple algorithms and heuristics that don't give any theoretical guarantees work very well. So we want to try to explain like why this is. So in our work, we're looking at sort of a beyond the worst case setting. So we're going to make some assumption on our input. And the assumption we're making is that the input is stable. And so what that means for us is that if you perturb the input points, the optimal clustering will stay the same. And so what I mean by that is that the actual points in each optimal cluster will be the same after this perturbation. So you can change pairwise distances by some small amount. And if you find the optimal clustering, it will be the same. Right, so maybe you can see that if we move these points slightly, the optimal partition will still be exactly the same. So intuitively, what this means is that the optimal solution should be easier to find because it satisfies this stability property. More formally, the stability property, we say that an instance is alpha stable if the optimal partition doesn't change when we can modify pairwise distances by at most an alpha factor. And so you can do this independently for each distance. So this modified distance doesn't even necessarily need to be a metric anymore. And again, the intuition is when alpha is large or when you can change distances a lot, the instance is very stable, and presumably we can find the optimal solution in polynomial time. And this is indeed the case. So previous work has shown that when alpha is at least 2 in general metrics, the exact solution can be found in polynomial time. And then if you have a fixed doubling dimension, you can actually lower this value of alpha, the assumption to be 1 plus epsilon. And in general metrics, when alpha is less than 2, this problem remains NP hard. And so all this previous work is sort of focusing on minimizing the value of alpha you need to assume so that you can design exact polynomial time algorithms. So previous work gets this alpha all the way down to 2. But in our work, we're more interested in seeing what value of alpha we would need to assume that we have in order to design a fast algorithm and still find the optimal solution. So in our work, we want to find a near linear time algorithm. Right, so I'll briefly go over our results, and obviously we talk more in depth about this in the longer talk online if you're interested. But again, we're in Euclidean space, and for fixed dimension D, for all three problems, we can solve the problem in near linear time using a simple dynamic program when alpha is at least 2 plus root 3 plus epsilon. And so this tilde notation is just hiding logarithmic factors. And so what we show is that the optimal clusters are actually subtrees of the MST, and you can design a dynamic program to basically find these optimal clusters in near linear time. And then for K-median, we also show that when alpha is at greater than 5, then we can also solve this problem using local search in near linear time. And so in both of these results, sort of one of the challenges to doing this in near linear time is the fact that we need to find the cost of candidate clusterings quickly, because if we just naively compute the cost of a clustering, then there may be a linear number of clusters we need to consider, and our runtime will be quadratic. So in order to do this, we sort of use some data structures and some properties of stability that allow us to do this faster. Right, and again, the details are sort of in the longer talk. Are there any questions?
So what is a local search algorithm?
Right, so this local search algorithm is just a very simple one swap. So you start with any solution. So you pick k input points and say that this is our solution. And then in each step, you drop one center and you add the input point that decreases the cost of the clustering the most. And you continue to do this while the cost of the clustering decreases.
But does it make sense to ask that for k-means and k-center as well?
Right, so this actually also works for k-means, but the alpha has to be larger just because of this square of distances. You need the alpha to be 9. So I think like one of the most interesting extensions of this would be to lower the value of alpha we assume, because right now it's quite high in comparison to previous work. But I think to speed up previous algorithms or to design new fast algorithms, we sort of need some new idea.
Okay, thank you. Are there any other questions? We still have about 2-3 minutes. Okay, so if there are no questions, we thank Erin again and move on to the next talk. This is by Karthik Kajulapalli, James Leo, Tung Ma, and Vijay Vazirani. And the talk is on stability preserving time efficient mechanisms for school choice in 2 rounds. And Karthik is going to give the talk. Over to you, Karthik.
Hi, everybody. So this paper is about stable matching in the context of school choice, but it's really just, I mean, school choice is just one application. I think can be applied anywhere. I think these are just properties of stable matchings we explore. And this is joint work with James Lutung Vajirani at UCI. Okay, so let's just, I mean, I think this is the last stable matching talk. We've seen a lot so far, but I'll just recap it again. So you have a set of n boys and n girls, and each boy has some total ordering over the girls, and each girl has some total ordering over the boys. And a matching is considered stable if there's no blocking pairs. What this basically means is there's no boy and girl who are not matched to each other, but prefer each other over their partners in the matching. So let's just look at a quick example. So imagine like boy 1 likes girl 2 over girl 1 over girl 3, and girl 1 likes boy 1 over boy 2 over boy 3, and so on. We define preferences like above. And so if you look at the matching, the first matching, boy 1 is matched to girl 1 and boy 2 is matched to girl 2, and this is like a perfect matching. But boy 1 likes girl 2 over girl 1, and girl 1 likes girl 2 likes boy 1 over boy 2. So in some sense, these guys, boy 1 and girl 2 will run away from this matching because they're happy together over this matching itself. And if you look at the matching in B, there's no pair of people who together are happy, so nobody will run away. There's no pair that will run away. Some people individually may be unhappy, but as a pair, nobody can run away. So that's the idea of stable matchings. And so when you apply this to a more general setting, which like we'll say school choice, you have a set of schools H, a set of students S. And so now we generalize it even further. We say we allow incomplete lists. What this just means is if there's some schools I don't want to attend, I'll put the empty set before that and say that, okay, anything that comes after the empty set in my list, I will just not go there. Just match me to the empty set instead. And there's some preferences over the students too. So this could be something like proximity to schools, or if I have a sibling in the school already, the student has more preference over somebody else. So schools also compute some total order. And each school has a capacity in terms of how many students it can admit, right? So this is a natural setting, and this is the setting that is used in school districts in Boston and Chicago. So it's very applicable if we can come up with good mechanisms for this kind of system. Okay, and so now we're moving from like a one-to-one to like a many-to-one. We also have to update our definition of a blocking pair, but it just follows naturally from the previous definition. Okay. So what is the classical setting is I have the setting mentioned above, and I compute this stable matching over this, some pseudo-optimal stable matching. And then I do this every year, and I keep going, right? So what we ask is what happens if certain parameters of your matching change, or you want to compute some objectives over your original matching, right? So you want to, some things change, like for example, new schools arrive or new students arrive, right? So matching is no longer stable if you just send them to arbitrary schools. So under certain parameters changing in your original matching, what results can you get? And so we kind of divide ourselves into three categories. Type A is asking, so in round 1 you compute a stable matching, and in round 2 you have to compute another stable matching. But the goal is that if a student is matched to a school in round 1, he must be matched to the same school in round 2, right? So it's kind of like an extension. You can't change the match of anybody. You can only increase the size of the matching. And this will make more sense in a second. I'll be more explicit about the different settings. Type B is saying that, okay, so now in round 1 you have a matching that's stable, and in round 2 you have a matching that's stable. And now we allow some people to be moved around. So I could be matched to some school in round 1 and a different school in round 2. But we want to minimize the number of students who are moved like this. And type C is just saying that some functions, so like some objectives we want are just unachievable. They're just NP hard. Right, so these are the three kinds of results we have. So let's just do like so setting A1, this is just one of the type A results. And this is a simpler setting, I think. You compute a student optimal stable matching in round 1. And there are a bunch of students L who are left over, right? So these guys just didn't get matched because maybe the school just had small capacity. Okay, so now the question is there any way of, suppose we can magically, assign capacity, increase the capacities of certain schools? Is there any way of, so how do we assign capacity to schools so that we can maybe match some students in L into this matching, right? So is there any way of adding them to the matching? And the answer, yes, there exists a polynomial time mechanism that does this. And just for now, you guys can believe me, and I go over it in more detail in the full version of the talk. But okay, so setting A2 is adding a layer of difficulty to this. So now it's not just that they're leftover students, but it's a new set of students arrive in round 2, right? And so already there are problems because when new students arrive, this could automatically induce blocking pairs in the original matching. And so the first question is, okay, so I have to match some of these because otherwise they'll be blocking pairs. And so we ask, if we minimize the number of students we match, the new students we match, subject to this, can we maximize the number of L? And the criteria again that we're trying to satisfy is that anybody matched in the first round has to be matched to the same school in the second round, right? And we provide polynomial time mechanisms for this. But for some problems so we kind of play around with the parameters like minimizing N subject to maximizing L, maximizing N subject to minimizing L, all these different criteria, and we kind of see that some of them are actually NP hard. So if I wanted to maximize the number of students in L, and then subject to this minimize the number of students in N who I admit, this basically ends up becoming some kind of set cover problem and is NP hard. And so I get like a bunch of naturally occurring problems that turn out to be NP hard. And I think that's kind of interesting that Yeah, these just crop up out of just a small change causes like, problem to suddenly become NP hard, right? Okay. So this is the kind of like type of results we have. Type B, I think, is a much more natural setting, which is, or much easier to state rather, which is in round one, I have a stable matching, and in round two, new schools arrive, right? And so when new schools arrive, maybe I want to move to this new school because I like it more. But when I leave, I create a vacant seat in my school, and somebody else wants to come there. And so I have this like cycle of people wanting to move up the ladder. And the question we ask is, can we compute a stable matching that is stable with the addition of new schools, but minimizes the number of people who change their schools, right? So, and a natural approach maybe is to try Gale-Shapley on this new instance, but we kind of show that that doesn't work. So we need to do something different, and we provide a different mechanism for doing this. More interestingly, though, what we show is that there's actually a very nice structure within so there could be many different possible, we call these minimum stable reallocations. And that there's actually some very nice structure in here. And that is that the set of minimum stable reallocations actually form a lattice. And the way to see this is actually a core lemma, which is that the set of students who have to move are the same in all solutions. And once you're able to realize that, you can define like a special stable matching instance over these students. And since all stable matching instances have a lattice, you kind of get like a sublattice of the whole problem. So that's kind of a neat result. The algorithms itself are actually quite simple. You just resolve blocking pairs as they come. And so the symmetric version of this is instead of new schools, new students arrive in round two. So that's setting B2. And again, the mechanism is very similar. And the way I would say you can see this is, imagine you have a bipartite graph, because we can reduce any many-to-one stable matching to a one-to-one stable matching instance. And so if you have a bipartite graph, it just you could think of this as having like one side of the bipartition arrive in the second round with a set of edges, and now you're trying to find a stable matching with this in this new graph. And so in the second setting B2, just that the side of the bipartition the nodes are coming from is the opposite side. So the problem is still symmetric, and so the analysis kind of follows from there. And so I'll leave with some open problems. The negative result is that the algorithms we propose are not incentive compatible. But what's stronger is that for the settings we define, there can be no incentive compatible mechanisms. And that's not good, because then we can't apply them in practice. If they're not incentive compatible just means that being honest is like a good strategy. And if mechanisms are not incentive compatible, they cannot be applied in practice, which is not a good thing. And I think one of the biggest problems is we allow lists in our preference list to be incomplete. And I think that allows people to cheat in certain ways, and the examples we have in the paper. But maybe allowing complete preference lists allows the construction of incentive compatible mechanisms. I think that's one interesting direction. The second one is designing approximation algorithms for the NP-hard problems. So there are a few more NP-hard problems I'm not mentioned here, but all NP-hard problems kind of reduce to this kind of special set cover instance where if you pick an element, you don't have to pay for it again. So it's kind of like a more generalized set cover. So I think the problem itself is of independent interest. And yeah, so I'll leave there. And thank you guys. If there are any questions, I'll stick around.
Thank you. Are there any questions?
Hi.
Mm-hmm.
So I wanted to ask, in the type 2, you are not minimizing or maximizing the number of students who are moving, right? Like there is
no. So in type 2 results, we're not really we don't care about capacity. The capacity is fixed. You could think of it like that.
Okay, so then is it probably I misunderstood, or maybe it's correct. So is it a valid algorithm for type 2 that you just find a new stable matching, or suppose a student optimal stable matching for after the new schools arrive, and that's a solution?
No. So the problem with that is if you just apply new student matching, you could actually perform extra reallocation. So you want to so the constraint is you want to minimize. So there were some people who were matched in round 1, right? And in round 2,
you do want to minimize the number of reallocations.
Yeah, you want to minimize the number of reallocations. That's the constraint.
Okay.
Yeah.
Okay. But in type C, which is your hard version, there you want to minimize the number of reallocations as well as maximize something.
So yeah, for those ones, there are a bunch of different criteria we're given. There's not just one, but that's one of them, right? So one of them is like maximize the number of students in L who are matched, and subject to that minimize N. but there are a bunch of different ones too. So
minimize what? Subject to that, minimize what?
Subject. So if you it goes back to the type A results, and you want to maximize the number of students in L. So get as many students in L as you can, and subject to this, minimize the number of students in N who you match.
I see. Okay. Okay. Thanks.
And on those questions, so what do you mean by approximation algorithm? What would you approximate when you have multiple?
So right now we're trying to minimize the number of students in N who are matched. So an approximate solution will be maybe matching more than the minimum. So if the optimal solution had like 5 students in N matched, the approximate solution may be like 5 log N or something. So maybe you match 10 students or something like that. So you match more people than you would have to from N. Yeah.
Sorry, just to confirm, this N and L are the sets, the old students and new students?
Yeah, L is the students who were not matched in round 1, but they were in the system. And N is a set of new students who arrived.
Yeah, okay.
Any other questions? I mean, we still have some time. Okay, if there are no more questions, we thank Karthik again.
Thank you, guys.
And we move on to the next talk by Joshua Cook on size bounds and low depth circuits for promise majority. Yeah.
Share. Okay. Okay, can you see the screen?
Yes.
Okay, so yeah, so I'm going to talk about size bounds on low depth circuits for promise majority. So first, let's go over what promise majority is. So promise majority is just a promise version of majority, where it'll output the majority of the input bits, promise that most of the input bits are either 0 or 1. So it's parameterized by this epsilon. So if at most epsilon fraction of the bits are 1, it'll output a 0. If only at most an epsilon fraction of the bits are 0, it'll output a 1. And we're not guaranteed what it'll output if it's somewhere close to half. So this is an important problem because it's often usable in place of majority in certain algorithms, for instance, in circuit de-randomization. And it's widely studied and it's computable in AC0. AC0 and other simple models of computation famously can't compute majority. So what's AC0? AC0 are alternating circuits that have and OR gates that have unbounded fan-in. The layers alternate between being ANDs and ORs. The bottom layers can potentially include negated inputs. And then the size is the number of gates. Sometimes you also define the size as the number of wires, though in our case, the results are similar either way. Then AC0 are the class of circuits that have constant depth and polynomial size. Okay, so we proved several results in this paper, but we're going to focus on the circuit lower bounds since those were the most involved results. So you have a trivial lower bound that you need a linear number of gates. So we're suppressing some polylogarithmic factors here for convenience. So you need a linear number of gates because you can destroy one gate by fixing one variable. And you can't have fixed the value of the circuit with fixing fewer than epsilon in variables. Then in 96, Chaudhary and Radhakrishnan proved that you actually need slightly more than linear. In 2011, Viola showed that as your epsilon fraction approaches 1/2, you actually need bigger and bigger circuits approaching an exponential like this. So what we proved in this paper is that actually for like moderate sized epsilons, so for all constant epsilons that aren't close to 1/2, you need, greater than quadratic size circuits approaching quadratic as epsilon goes to 0. And if you look, we prove slightly different but similar results for the monotone special case. And our lower bounds are close to the upper bounds that Aitai gave by his circuit in 1983. So we are focusing on depth 3 circuits here. So these lower bounds were only for depth 3 circuits. So one thing we should note is that if you have a promise majority circuit, its negation is also a promise majority circuit. So we can just assume that the lowest level of gates are all AND gates. So we're just going to call the input bits variables, the first level gates clauses, the second level gates DNFs, and the third level gate is just going to be our circuit, which is just going to be a conjunction of DNFs. Okay. A couple of tools we need to use here is we're going to use the inputs that you used in a biased coin problem, which just independently sets every bit equal to 1 with probability epsilon. So as a simple example here, the probability of outputting all ones is on a d to the 1/3 input is going to just be 1/3 to the third. So 1/3 probability of this being a 1, 1/3 probability of this being a 1, 1/3 probability of this being a 1. So this is strongly related to promise majority because by essential limit theorem with probability almost 1/2, the epsilon will have less than epsilon fractions of ones. So they're very closely related problems. And the key tool we're going to use to actually prove these lower bounds is restrictions, which is fairly standard. And the basic idea of a restriction is it's going to have ones, stars, and zeros. And if there's a 1, then we replace the input with the 1. If it's a star, we leave it as a variable. If it's a 0, we replace it with 0. So for example, if this is our circuit and we're applying this restriction, we put the variables in, and if a clause, all of the variables in it are set to 1, that clause will be set to 1. If a DNF has a clause in it that's set to 1, that DNF will be set to 1. If one of the variables in a clause is a 0, it'll be set to 0. And once a gate has been fixed, then it can be removed. So that's the basic way that we actually eliminate gates to simplify our circuit. Okay. So the idea to actually prove the lower bounds is that we are going to basically lower bound the fan-in at each layer. So a result from Viola in 2011, he basically showed that problem-solving promise majority has a clause size that is log n over log of 1 over epsilon. Then we use this with a greedy set cover algorithm to actually show that our DNFs have to have in size n to the 1 plus alpha, whereas alpha is this constant that's based off epsilon. And then we can use, again, the same greedy set cover algorithm in a slightly different way to show that the circuit has to have size n to the 2 plus alpha. Okay, so the greedy set cover algorithm that we use basically says that if we have m sets and each one of the sets is pretty big, it has this width w, then we can find some subset t such that the number of clauses it doesn't intersect, the number of sets it doesn't intersect with S decreases exponentially in the width of the sets and the size of the t that we're hitting them with. In particular, this is useful because if we have a monotone DNF F, we can find a restriction that restricts it, and it will decrease the size of F exponentially in the width and the t, the width and the size of the restriction divided by n. Okay, so that's the basic tool that we use, and how do we actually use it? So we would like to actually just say that we can just say this, the DNFs have to have this size, but we can't always say that because we might get in some nasty cases where we have some small DNFs that don't do anything. But that's where the d epsilon comes in. So if we assume that we have a DNF that always outputs 1 whenever we have mostly ones in our inputs, which all of our DNFs will have to have in order for our circuit to satisfy promise majority, and we assume that on d epsilon it has a non-trivial, so polynomial, chance of outputting 0, which the DNFs that are sort of going to help us compute promise majority very much are going to have, then we can prove that F has to have a size into the 1 plus alpha. And the basic way we do this is by using the greedy set cover algorithm. And then we use the greedy set cover algorithm again here to lower bound the circuit size. And basically the idea is that we are going to fix entire clauses to just get rid of DNFs. And if there's not enough clauses, then we can too easily eliminate all the DNFs. Right. So yeah, this is what I just said. So first we move all the large clauses. So that way we can fix a clause using few variables. We can do that again with a greedy set cover algorithm. Then using the DNF lower bounds, we can get that we can look at the DNFs that are bigger than +1 over alpha. Then we can fix whole clauses to get rid of DNFs. If there are few clauses, then the DNFs must share the clauses too many times, so we can eliminate too many DNFs. So there either are a lot of DNFs or a lot of clauses. And again, some DNFs might be small, but we focus on the large DNFs during the elimination, and then some large DNFs have to survive if we only fixed a few variables. Okay, so that all assumed that it was monotone, but in general, our circuits might not be monotone. So how do we handle that? And we do the same basic thing. So our clause lower bounds from Viola actually are still fine, they still work. The DNF lower bounds almost work, but we have a slight concern that the DNF might be set to 1 early because whenever we're doing these adversarial restrictions where we're trying to do the clause set cover, the negations might actually make us set the DNF to 1 early. That's a concern that we have, but we can bypass this. And then the arguments for the total circuit lower bound still work. Okay, so how do we fix the issue with lower bounding the DNF size in the general case? Well, the idea is that we are going to basically sample from d epsilon, but we're going to do it bit by bit. So we're going to still basically choose the bits that would be included in the greedy set cover algorithm and fix it, but instead of always fixing it to 0 to eliminate clauses, we'll sample it from d epsilon. Then it has a good chance of eliminating the clauses. And then we focus on only deleting the clauses bigger than W. Then we can use a greedy set cover algorithm to choose variables just like the monotone case. And then by a turnoff bound, it's likely that we'll eliminate many of the clauses. And by definition, restricting the rest of the variables is the same as d epsilon. So it's unlikely that we've accidentally fixed the DNF to 1 because it had a good chance of recognizing it and being 0. Okay, so that's an overview of how we proved the lower bounds. You can check the full talk for more details or read the paper. So here's sort of an overview of the state of the art in the terms of the depth 3 bounds. So we have a trivial bound for n. Itai gave this upper bound for the of the green line. Then Chaudhry and Radhakrishnan showed the slightly better lower bound. In 09, Viola proved some uniform circuits for doing this. And then in 2011, he showed these lower bounds for circuits doing it. Then we, in this result, showed these new lower bounds for the monotone case here and lower bounds for the general case here. So this area here, it's sort of unknown which way, where the optimal circuit size is. We also slightly improved uniform circuits as an additional result. So we have roughly cubic size uniform circuits as well. So there's also an open problem of finding uniform circuits that compute promise majority with optimal size. All right, that's all I have to say. Any questions?
Yeah, so Ram Prasad has a question. You want to speak?
Yeah. Hi. So in this graph, sorry, which of them are upper bounds and which of them are lower bounds?
The blue and the green ones are upper bounds, and
I see.
everything else is lower bounds.
And do we know of better upper bounds if we are allowed to use negation gates for depth-3 circuits computing these promise majorities?
So the negation, so basically when you do AC0, you use De Morgan's to sort of push the negation gates down into the variables. So the lower bounds for the general case actually includes negation. It's the same depth and the same size.
I was wondering with regard to the upper bounds, like do we have slightly better upper bounds if we are allowed to use negation of literals as leaves?
I don't think that we know of any ways to use negations to improve the circuits. To my knowledge, no. And I'm pretty sure the answer is no. So we don't know whether or not it helps. It doesn't seem to me like it would help. Yeah. It's a good open problem, though.
Jaykumar has a question.
So what is known for other depths beyond 3?
Right. So there's also, we do have basically, and it's explored in the Fuller paper, as your depth increases, both the optimal size and so both our lower bounds and our upper bounds go down to 1 in sort of a into the 1 plus some fraction to the depth. The paper gives some specific upper bounds by basically giving a recursive construction of ITI circuit. But we don't have, okay, so I assume you're the same Radhakrishnan from the 96 paper?
I have the same old one, yeah.
Yeah. So your results for the lower bounds, we didn't improve on, but we did have some slightly improved upper bounds in terms of how quickly we go down to 1, but they're not tight. So basically the fraction, there's like a 1/4 for the proved lower bounds, and the upper bounds we have are like 1 to the square root of 2 to the depth for the fraction.
Thank you.
Yep.
Are there any other questions? Otherwise, we thank Joshua again and move on to the next talk.
Stop.
Yeah. So the next talk is by Shreyas Pai, and he's going to talk about connectivity, lower bounds, and broadcast congested click, co-authored with Sriram Pemaraj. Shreyas.
I think you're muted if you're talking.
Yeah, Shreyas, you have to unmute.
Sorry about that. Yeah, hello everyone. I'm Shreyas, and this is joint work with Sriram Pemaraju, who is my advisor at the University of Iowa. A full version of this paper is available on arXiv. The link is at the bottom of the screen. So in this paper, we consider the BCC1 model, which is a distributed model of computation. It stands for the broadcast congested clique with 1 bit of bandwidth. So we're given a synchronous all-to-all communication network with n vertices. The nodes in this network are machines, and the edges denote the communication edges, communication links. The The constraint here is that the nodes can broadcast only one bit in each round. And the input graph is a subgraph of the communication network. In this talk, the dashed edges will denote the network edges only, and the bold edges will be the input graph edges as well as the network edges. So the input graph is distributed in such a way that each node kind of knows it in a distributed fashion. So each node, first of all, knows which of its n-1 incident network edges are also the input graph edges. And each node has a unique O of log n bit ID, which it can use to identify itself. And the nodes are interested in computing graph properties such as connectivity, where they want to know if the input graph is connected or not, and connected components, where they want to find which connected component they belong to in the input graph. So initial knowledge plays a very important role in these models. So you can define it in two ways. One is the KT0, which is the port model, where the nodes only know their own IDs initially. And this other way to define it is the KT1 version, where the nodes know the IDs of all the nodes in the network. So because we can only broadcast one bit in each round, you need O of log n rounds to go from KT0 to KT1. And this difference is not trivial. It, in fact, requires us to use different lower bound techniques. So for connectivity in the broadcast congested clique with 1 bit bandwidth, the best known KT0 and KT1 algorithm runs in log squared n over log n rounds. This is a result by Judinsky and Nowicki. And the best known lower bound for connectivity is log star n rounds. This also holds in the KT1 model. So the question we ask is, can we show a better lower bound for connectivity in the BCC1 model? And our results in this paper are that in the KT0 model, we show a randomized omega log n lower bound for connectivity, which holds for constant error protocols. And in KT1, we show a deterministic log n lower bound for connectivity and a randomized log n lower bound for connected components. Note that a lower bound for connectivity implies a lower bound for connected components, but not the other way around. So our randomized lower bound for connected components doesn't imply anything for connectivity. So the KT0 lower bound uses a technique called edge crossings, and this is the main technical contribution of this paper. I won't have enough time to talk about this lower bound. You can take a look at the YouTube video or the paper for more details. The connected components lower bound uses information theoretic techniques. You can take a look at our paper as well for this. In this short talk, I will describe this deterministic log n lower bound in the KT1 model. So recall that in the KT1 model, the main thing is that the nodes know the IDs of all of the other nodes. So what we use as a lower bound technique is reductions from two-party communication complexity. In this two-party communication complexity, you have two players, Alice and Bob. Alice receives a private input X, Bob receives a private input Y, and they want to compute some joint function f of X and Y. So the way two-party reductions would work is you want to reduce connectivity to computing some f of xy, some function f over the private inputs. So Alice and Bob, they get their private inputs x and y, and what they do is they use these private inputs to create an all-to-all communication network with an input graph, such that Alice will simulate the blue vertices on the left, and Bob will simulate the red vertices on the right. And what they will do is they will simulate a BCC1 algorithm on this communication network, such that at the end they will get the value of f of x comma y. And because each node broadcasts a single bit in each round, the BCC1 lower bound that you get is at least the communication complexity of f divided by the number of vertices. So two-party reductions from set disjointness have been used to show lower bounds for subgraph detection in BCC1. This is a paper by Drucker, Kuhn, and Oshman. They show omega n lower bounds for detecting cliques of size greater than 4, and square root of n lower bound for detecting complete bipartite graphs. But connectivity, on the other hand, is a much easier problem. It can be solved in log squared and over log n rounds, and reductions from set disjointness don't quite work in this case. So what is a candidate hard problem we can use? I propose something here which I call the perfect matching problem. Here, Alice is given a perfect matching on a set of vertices. These are the blue edges. And Bob is given a red perfect matching on the same set of vertices. And the question that they want to ask is the graph with the red and blue edges connected or not. In this example that I've shown, this graph with the red and blue edges forms a single cycle. But in general, you can imagine that it can form a graph with many cycles as connected components. So using a very old result by Hajnal, Mas, and Turan, we can show that the deterministic communication complexity of this perfect matching problem is omega n log n. And we also show how to reduce this perfect matching problem to connectivity. And this immediately gives us a KT1 BCC1 lower bound of omega log n rounds, because we divide the communication complexity by n, which is the number of vertices. So a few open problems that I would like to stop with are that, first of all, we only are able to show that the deterministic communication complexity of perfect matching problem is n log n. Can we show the same for the randomized communication complexity? This we haven't been able to show this, so this is a very nice open problem, very nice and concise open problem that is unsolved by this work. Second is, can we close the gap for connectivity in BCC1? So the current lower bound that we have and the upper bound have a log n over log n factor difference. And thirdly, can we say anything about unicast model with 1-bit bandwidth? So in the unicast model, you can basically send a different 1-bit message to each of your neighbors. So the best algorithm that we know takes O of log n rounds. And in this model, no super constant lower bounds are known. Maybe we can also show constant round algorithms in this case. And I'll thank you and take any questions you might have.
Thank you. Are there any questions to Shreyas? Okay, there is a question from Sushanta Karmarkar. KT1.
So the question is, does KT1 means one hop neighbors or all nodes? So because the communication network is a clique, one hop neighbors is all nodes. So both are equivalent, at least in this case.
Hi, can I ask a question? Hi, I'm Arkadev. So I'm just trying to recall. So isn't it true that in the unicast model for this click thing, if you prove, so there's a barrier, right? There's a circuit complexity barrier. If you prove super something, then you get circuit lower bounds that are not known.
Yes. So to my knowledge, that doesn't quite seem to apply for 1-bit bandwidth. That applies for log n bit bandwidth.
Oh, right.
Yeah. So super constant lower bound in the 1-bit bandwidth wouldn't give any meaningful lower bounds for log n bit bandwidth. So I don't think the connection is formally known yet.
Okay, if there are no more questions, we thank Shreyas and also all the speakers of this session. Virtual applause. And we meet again at 8:30 Indian time for the next talk. And until then, participants are welcome to discuss, I believe, in the Slack space. Thank you all and see you at 8:30.
Yes, thank you, Venkatesh, for chairing the session, and thanks to all the speakers from my behalf also. So as we'll be meeting again at 8:30. Until then, I mean, you are welcome to continue the social interactions if you want and gather. Okay. So
Okay.
So with that, we'll wrap up this session. Okay, bye.